Hi, so it's just been brought to my attention that I don't have a video about F-tests. So here I'm going to talk about that. What do they test and how do they relate to t-tests? So firstly, are you prepared for this? You might want to review the multiple linear regression video using matrix math, as well as the contrast and linear models. In addition, perhaps the ANOVA video, the one-way ANOVA with 3 levels, because that is the model I will be building off of here. So here's what that model would look like, the one-way ANOVA with 3 levels. So I have 3 observations per level. The first 3 are level 1, second 3 are level 2, last 3 are level 3. This is not a repeated measures model. So I have 9 independent subjects that I'm modeling here. I'm using what I refer to, well, not me, I didn't make it up, but what's called the cell means approach for the model. So the first regressor is the mean for level 1, second regressor is the mean for level 2, and third is for level 2, 3. And therefore the parameters beta 1, 2, and 3 are the means for levels 1, 2, and 3 respectively. So the beauty of F-test is they simultaneously test multiple contrasts at once. So for example, if you're planning on running 3 separate t-tests, it's a good idea to start with the F-test because the omnibus test, if not significant, would indicate that you're done and you wouldn't have to do further testing. So it's a way to cut down on multiple comparisons. And additionally, sometimes there are hypotheses that you can only test with an F-test. So for example, if you want to test if any of the levels are different from each other, so if your null is that the 3 levels are equal, so the mean for level 1 is equal to level 2 is equal to level 3, notably here I did not put equal to 0, just that they're equal, so they could all be equal to the same non-zero value. So in this case, rejection of this null implies at least one difference. Either levels 1 and 2 differ, or 1 and 3, or 2 and 3. So this test would require an F test, as opposed to a t-test. F-tests use contrast matrices, whereas t-tests, as you'll recall, you have a contrast vector. You typically write out a row vector. So I'm going to give some tips for constructing the matrix. You start with your null hypothesis. So in this case, my null is that level 1 equals level 2 equals level 3. And then much like the t-test, we need to get a 0 on the end. So what I'm going to do here is I'm going to subtract level 3 from all parts and break it up. So it's equivalent to level 1 minus level 3 equaling level 2 minus level 3 equaling 0. So this is an equivalent hypothesis to the first one I have. And now you can break it up. So you can see we effectively have 2 separate contrasts here, which put together, if tested simultaneously, comprise our F-test. So those 2 are whether level 1 minus level 3 equals 0 and level 2 minus level 3 equals 0. And that gives you your alternative. Level 1 minus level 3 equals 0, or level 2 minus level 3 equals 0. You might be thinking, whoa, what about that other case, level 1 minus level 2? That's inherently included in these 2. Then once you have that, you create a contrast matrix. You basically construct the contrast for either or for both of these, and you stack them on top of each other. So in that case, it would look like this. Here's level 1 minus level 3, level 2 minus level 3. So again, level 1 minus level 3, level 2 minus level 3, you would put those 2 contrasts together and stack them. So this would be beta 1 minus beta 3, beta 2 minus beta 3, if you multiplied it out. So just a quick review of t-tests when you're using a contrast. The structure of the t-test is the contrast in the numerator divided by the variance estimate of that contrast in the denominator, which looks like this in matrix form. So this is, again, instead of a matrix, this is just a row vector, which should be 1 by p. So in this case, p would be 3 because I have 3 parameters in the model. And then x transpose x inverse, this would be 3 by 3, or p by p, x transpose y. So this is c beta hat up here. And then this is the variance estimate of c beta hat. And sigma hat squared is just the residual variance. The F statistic has a similar structure. It still has this mean divided by variance structure, but it's done with matrices, so it looks a little bit differently. So the F is, so just to explain how it's different, this is basically the denominator, so this part right here that's inverted corresponds to this part of the t-statistic, and then these two bits here correspond to the numerator. So we have our C beta hat transpose. Now C is that matrix I was talking about earlier. So if your the contrast matrix I showed earlier was 2 by 3, so C transpose beta hat will end up being a 2 by 1 vector. So this is a 2 by 1 row vector. This part in here, it looks very similar to the denominator up here, except there are a couple of extra pieces. Basically this R. R is just the rank of your contrast matrix. So in this case, R would be 2. It's the number of rows. So anyway, you have C transpose X C times R sigma hat squared. So R is a scalar and sigma hat squared is a scalar. The rest of this boils down to something that's 2 by 2. And last, this is the same thing that was here, but it is 2 by 1. So at the end of the day, you end up with a scalar. So just again, this part right here is an R by P contrast matrix where R is the number of rows of C and P is the number of columns in X, or the number of parameters in your beta vector. And then you have R itself right here. So this is R by P contrast matrix here, here, and here, which means after doing the multiplication and transposing, this is 1 by R. This is R by R, and this is R by 1. R is the number of rows in C, which I already said, and then the degrees of freedom. F statistics have 2 degrees of freedom, numerator and denominator. So the numerator degrees of freedom are R, and the denominator are N minus P. And then you would compare that to an F distribution with those degrees of freedom. So does this boil down to a scalar or a matrix? The answer to that, I was trying to lead you to that earlier, is it's a scalar. You do get a single number at the end of the day. So when is an f-test a t-test? When R is a row, just one row. R is 1, so your contrast matrix has 1 row. And you can use this in place of a two-sided t-test. So most fMRI-based software packages that we have don't run two-sided t-tests, but you can run one if you want by just specifying a contrast with a single contrast vector in it. And you will get the equivalent p-value as you would get to a two-sided t-test, which is really handy. Again, cutting down on the number of tests that you're running. Right, so uses for f-tests, you cut down on multiple comparisons. Instead of running 3 separate t-tests, which is what I would have had to do for my level 1 versus level 2, level 1 versus level 3, level 2 versus level 3 example, I would run 1 f-test. If the f-test is significant, then I can look at those separate t-tests to figure out what's happening. But if it isn't significant, I'm done and I can move on. So I only have 1 test to report. If an f-test, right, and so one thing I've noticed happening on the FSL list is people were running the f-tests and it wouldn't be significant, and then they'd look at the t-test anyway and they would be significant. So they were like, wait a minute, maybe I don't want to run these f-tests in lieu of running the separate t-tests because something might be significant in the t-test that I'm missing. So I want to talk about that. So I'm going to use a simpler example. So let's just assume we have 2 levels. And I'm doing the other type of f-test where I just want to know if either of the level means are different from 0. So is the mean for level 1 equal to 0? Is the mean for level 2 equal to 0? So my F contrast for that would look like this. Again, I'm assuming I only have 2 levels in the model instead of 3. If I was applying this contrast to the model I showed before, I would have to add another 0 here and another 0 here for the beta 3 parameter. So what I'm going to do is compare the 2 separate t-tests to the 1 f-test. The hope is that if the f-test is significant, at least one of the t-tests is significant, because that's our basic understanding of how the f-test works. And we'll see that's not the case, so that's the surprise. So the way this works is we have our beta 1 parameter values here, the beta 2 values here. Within this circle, the f-test, okay, here, I have it here. So outside of these lines, the t-test for beta 1 is significant. So here's beta 1 on this axis. Those are the magnitudes of beta 1. So to here or to here, t-test for beta 1 is significant. Above or below these two lines, the t-test for beta 2 is significant. And then outside the circle, the f-test is significant. So there's a lot going on here. So let's focus on some of these different regions. If I go in this region where this red dot is up here, all tests are significant. So beta 1 statistically significant with my t-test, beta 2 statistically significant with the t-test, and my f-test was significant. And again, the significant f-test would just indicate that one or the other was significant. So right there, everything works as we would expect. Here we have the f significant and the t for beta 1 is significant. So again, that's what we would expect. If the f statistic is significant, we would assume one or the other were significant, and then we would look at the separate test to see what's going on. And in the middle, nothing significant. Again, behaving as we would expect. But over here, and in similar regions that look like this, the f isn't significant, but the t-test is. So here we can see we're on the inside of the circle, so our f-test would not be significant. But if we were to look at our t statistic for beta 1, it would be statistically significant. And then in this little tiny kind of triangular region here, you can see the f is significant, but the t's are not. So you might be wondering, well, those last two cases, do they ever really happen? Indeed, they do. That's why I looked into it, because I kept seeing people asking about it on the FSL list. And pretty much when that happens, it's when you're riding that p equal to 0.05 edge. So I mean, you can report both and just put it's not a very solid effect. But still, not a bad idea to run the f-test. I wouldn't let these weird cases dissuade you from running the f-test, because really if you miss something that's statistically significant with the t-test that isn't with the f-test, it's a very weak effect. So that's all I have here. If you have any questions, feel free to ask me on Twitter or on the Facebook group, Mumford Brain Stats. You can also ask in the comment section below, but I don't always get notified about those. So Twitter or the Facebook group are best. So thanks a lot and have a great day.